our electrolyte is 60% water, and electrolyte is taking 40 to 80% of the total cost of the battery. No one wants to ship water around the world. So as long as there is trigger demand in local country, we can start the battery assembling very easily in that country. And that will help every country to achieve its energy independence and to improve their energy security.
That one line reframes storage as more than a grid technology. It becomes an energy security and industrial strategy question. Good morning, good afternoon, or good evening, wherever you are in the world. This is Climate Confident, Stories and Strategies That Cut Emissions, episode 279, and I'm your host, Tom Raftery. My guest today is Min Tang, Director of International Business at Rongke Power, one of the world's leading vanadium flow battery companies. We talk about why long-duration storage is becoming critical as renewables scale, how flow batteries compare with lithium, and why safety, black start capability, lifetime cost, and local supply chains may matter just as much as headline battery price. So I started by asking Min to explain what vanadium flow batteries actually are and why they matter now. Min, welcome to the podcast. Would you like to introduce yourself?
Thank you. Thank you very much, Tom, for having me here. My name is Min, and I represent RKP, the world's largest vanadium flow battery manufacturer. I'm in charge of the international business. I'm leading the global expansion of this technology right now. And I'm proud to say that RKP, we are the largest manufacturer of vanadium flow battery, and also we are the leading innovator in this technology.
And for people who might be unaware, Min, can you give us a 101 on vanadium flow batteries? What are they? How are they different from lithium-ion batteries, for example, which most people are well familiar with at this point?
Well, it's not 101. It's a very basic introduction of us that we are doing on a daily basis. First of all, vanadium flow battery is an emerging technology, so it's okay that the people doesn't know about this technology. Vanadium flow battery actually originated from Australia. Professor Maria invented this technology back in 1980s. So it has been developed for more than 40 years, and now it's commercial ready. Compared to mainstream batteries like lithium batteries, vanadium flow battery do have some unique specifications, and there are some facts that make it different from other battery technologies. So first, this battery is based on water-based electrolytes, so that makes it super safe with no risk of thermal runaway or fire or any explosion. And secondly, this battery is designed to last for more than 25 years with 100% of initial capacity. So that means this battery can run up to more than 20,000 cycles without any degradation. And we have a commercial project that's up and running for more than 14 years to prove this. So we're not talking about some theoretic number in lab. We are talking about real world application with more than 25 years of a life with 100% of capacity retention. So this is a battery very suitable to be built as a power system infrastructure. And last, this battery has decoupled design of power units and the capacity units. So this battery, with longer duration, the capex will be cheaper per kilowatt hour. Because just like a car, when we want a car to run more mileage, we just need to add more gasoline in the tank. We do not need to buy a new engine. So that's apply the same to this battery. With longer duration, the capex will be cheaper. Combining together all of those three facts will contribute to the lower levelized cost of storage. And the lower levelized cost of storage will help us to use more affordable and more reliable renewable power supply.
And just when you say that the batteries can last for 20,000 cycles, how does that compare to lithium-ion batteries, for example? Because I think some lithium-ion batteries are between 5,000 and 10,000. Is that fair?
Yes, it's fair. And for lithium batteries, when we do apple-to-apple comparison, we need to know that lithium battery, all the cycle numbers, they are tested under certain temperature in a lab environment. And when we say we have 20,000 cycles, that means we are saying that this battery can run more than 20,000 cycles in most temperature range and in most environment. So if we compare to lithium battery, we can say we have no cycle number limit.
And again, just for clarification's sake, the vanadium flow batteries, because they're water-based, they're typically lower energy density than lithium-ion batteries, and probably take up more land as well, or more space. So they're good, for example, energy storage that's stationary, but you're not going to be putting a vanadium flow battery into your EV.
Yes, correct. We are not going to replace lithium battery. Actually, we are not competing with lithium battery because we are a long duration energy storage technology that targeting as infrastructure sector. This battery cannot be used on EV. This battery cannot be used on cell phone. So we are not really competing with lithium battery in most sectors. I would like to correct you a little bit on the footprint part. Yes, we
Okay.
have lower energy density, but for footprint, we are not necessarily bigger because for stationary battery stations, we need to consider safe distance as well. For lithium battery, there is safe distance required between containers. And that safe distance will take much more space than the space actually taken by batteries. But for our battery, since it's water-based, there's no safe distance required. This battery can be put back by back and it can be stacked. So for any project with more than 40 megawatt hour storage capacity, this technology will save some footprint compared to lithium batteries.
Good to know. Thank you. And has long duration energy storage become more urgent recently than it was 5-10 years ago now?
Yes, indeed. This is a very clear trend because right now, I think just last week or something, the Arena just published a report saying that renewable plus storage can provide more affordable electricity to our grid and to our end user compared to traditional power source. So that will definitely make renewable concentration increase. And we are already seeing clear trend that most countries right now, the renewable concentration are growing from 10% to 30%. And after passing 13%, it will become a different era because renewable are very fluctuating by nature on generation side. And that will create a lot of challenge for grid operators. For long duration energy storage, we are providing the resilience and also the effective load carrying capacity as required by the grid operators. For shorter durations, for 2 hours duration, it may not provide the required resilience of grid operators. But for longer duration, definitely we can provide a higher effective load carrying capacity. In addition, we see more and more distributed power supply use cases. For example, remote mining sites and some area with very expensive grid connection. Right now, with long duration energy storage, they have another option that they can have the generation on site, then plus a long duration energy storage, then they can enjoy 24 hours of stable renewable power supply without grid access. And also, this can replace the traditional diesel generators that's been used in that area. So it could be cheaper option, and also it's called to reduce the carbon emission. All of this can be achieved only there is commercial-ready long-duration energy storage technology.
And for grid scale, the trend towards longer duration energy storage, is that coming from curtailment, grid congestion, reliability, something else? The pressure is increasing for it. Where do you see that pressure coming from?
I would say first it comes from reliability. Curtailment is part of the reason, but not the majority, because curtailment can also be reduced by shorter duration energy storage. Reliability, that's the most pressure come from. And also our grid right now is facing fluctuating from power generation side, from power producers, because most producers are become renewables, and also from the load. So fluctuating on both sides do require longer duration energy storage for grid operators. And not to mention that we have many critical infrastructures or critical applications that require much more stability from the grid than before. For example, AI data centers. They just need lots of electricity and the load varies as they are calculating our current. that is increasing demand. And also beside AI data centers, we do see lots of traditional industrial users trying to use longer duration energy storage to minimize their electricity bill. Because our electricity price right now is fluctuating, and the fluctuation is much greater than before. So by applying longer duration energy storage, they will be able to catch every minute of the price fluctuating and help them to minimize their electricity bill. And also for standalone base station, they can participate in the electricity market by doing arbitrage, by catching every minute of the price fluctuating.
And what about geographically? Are you seeing differences in the requirement for storage in different energy markets?
Yes, definitely. Geographical difference is quite big. For example, you cannot expect the same battery to be used in Saudi Arabia, where they have the highest average temperature, and Canada, where they have probably much lower temperature range. So there will be very different technical requirements for different user cases, and also different renewable concentration. Also, the differences on power sources make different requirements on energy storage as well. For example, in France, they're mostly powered by nuclear, which is much more stable. So their investment on long duration energy storage could be deferred. Their demand on longer duration will be less compared to Australia, where they are going to renewables with higher percentage, but with limited capability to build pumped hydro stations. So in Australia, they need alternative to nuclear and to pumped hydro, which give vanadium flow batteries that's almost the only option there. That may apply to some parts of Europe as well. For example, in Spain, grid resilience could be a big topic there. And also in Spain, you have abundant solar. So in that area, I would say flow battery could be a very good option to improve the grid resilience and to improve the stability and to help the local power system to accept more renewables.
Okay. Seeing as you mentioned Spain and grid resilience, how are vanadium flow batteries when it comes to black starting grids in case there's a grid outage like we had last year?
Well, actually, vanadium flow battery is the first battery ever done grid scale black start experiment. No lithium battery has done that before. In June 2024, there is a vanadium flow battery station with 100 megawatt, 400 megawatt hour scale located in China, has done the grid scale black start experiment and witnessed by IEE and many international and professional organizations. Vanadium flow battery, this battery can overloading, so it can charge or discharge over its rated power without any safety concern. And also, it will not create any damage to the battery itself if the overloading is only for a short period of time. That will provide the resilience that grid operators need most during black start. And also, this station during daily operation can be used for peak shaving, for grid services, for ancillary services. So it have economical value during daily operation. During emergency, the power in there can be used to start ancillary system in coal-fired stations or gas stations. The battery can switch smoothly between grid following and grid forming mode. So that will help the local grid operators to operate the battery more flexibly and also provide them with more stability. And this battery can generate its revenue to sustain itself during daily operation. Compared to lithium battery, this battery and also the capacity in the station does not change over 25 years. For grid operators, they can always see there is, for example, its initial capacity as 400 megawatt hour. After 20 years, after 25 years, still have 400 megawatt hour. So the capacity does not degrade, and they always have enough resource for this grid level black start and also for the daily operation.
Okay. It's a pity it doesn't work for mobile phones because my mobile phone's at about 80% right now, where it was when I bought it.
Well, sorry, it doesn't work for mobile phones, and you definitely do not want to carry liquid in your mobile phone.
True. You mentioned Canada there, and that brings me to the thought, I know lithium-ion batteries in cold environments tend to not perform as well, but if vanadium flow batteries are water-based or have a lot of water in them, does that mean that there's a chance that they freeze up in very cold weather, or how do you manage that?
Well, the electrolyte used in vanadium flow battery do have 60% water, so it could freeze if you put it in idle status for a very long time in -10 or -20 degrees. But during the real operation of the battery, there is efficiency loss, and that efficiency loss creates heat, and that will keep the electrolyte above zero. So we do have actual commercial project deployed in area in China, in northern eastern China, in area even colder than Canada, where they have -35 winter. That project has been deployed and up and running for several years. There's no problem for getting frozen. Of course, we will provide a little bit extra heating in wintertime, but in general, the energy efficiency still look very good, and the performance of the battery does not impacted by the cold temperature. And also for hot temperature, this battery has an operating temperature range for environmental temperature from -40 to above 60, so which is much bigger than lithium batteries. Because in hotter temperatures, the lithium battery can easily get on fire, but this battery, because it's water, it's very hard to get on fire. You can never light up the electrolyte. And so even for hotter temperature, it's very hard to increase the temperature inside the battery because water do absorb more heat.
And then what about the economics? Because is there like a crossover point where vanadium flow batteries become more economic and more favorable to install rather than lithium ion?
Well, first of all, I want to emphasize again that we are not competing with lithium battery. We are different technology targeting at different user cases. There are some certain user cases we do have advantage. For example, with longer duration, with anything with more than 4 hours duration, this battery will be able to provide lower levelized cost of storage. So that means the electricity discharged from this battery will be cheaper than from other battery technologies. But of course, for project, the financial decision is always complicated. People have more considerations. For example, they need to look at IRR, they need to look at payback, sometimes they need to look at ROI. So there would be different factors or different parameters investors are looking for. So that will influence the investment decision. In general, this battery will provide lower levelized cost of storage in a scenario with more than 4 hours duration. And also, I would say in some certain areas, for example, chemical parks, you definitely cannot have a potential fire risk in there. So that will give a unique advantage for this technology because this technology does not have any fire risk. So it can be deployed in oil well, in gas field, in chemical parks, and it already has been commercially done. So there are scenarios for us. We are not going to compete with lithium. There will be different market for vanadium flow battery and lithium battery. And in some cases, we are also creating hybrid system using lithium and vanadium flow battery to deliver the lower levelized cost of storage. Because, for example, for EV charging, the battery may not need to be fully charged and fully discharged every time when there's a car come here to charge. So for the multiple cycles, flow battery can run more cycles. But when all the cars come in and occupy every charging lanes in their station, they require higher power, but for a very short period of time. Then that time, lithium battery can be used to charge those cars. But the lithium battery maybe probably only run 1 cycle or 0.5 cycle per day, but vanadium flow battery can run multiple cycles per day. So combining together, that will give longer service life to the lithium battery, and also in general, the levelized cost of storage for that station can be reduced and could be lower than just build the site by vanadium flow battery or lithium battery. A hybrid system could make more sense.
And we've seen with lithium-ion batteries that the cost of them has fallen 95% in the last 15 years. Are we seeing similar price drops in the cost of vanadium flow batteries? Is there a learning curve that makes the cost go down? Is there economies of scale that make the price go down as well? How is price working over time for vanadium flow batteries?
Well, from 2016 to 2026, within 10 years, the cost of vanadium flow battery has been reduced by more than 50%. The learning curve is very significant because we are still in early stage of commercialization. We only have 1 gigafactory, and we are the only one in the world. So we are expecting the cost to be further reduced with increase of the production scale and more complete supply chain. Because right now the supply chain, we can say we are commercial ready, but the supply chain part, we don't have too many suppliers. With the economy of scale, the cost will be reduced. And also this technology is very fastly evolving. We do see the energy, we call it current density in the stack, in our power units. Current density has been increased by more than 50% in the past 10 years. And we are further increasing the current density. So that will reduce the material we use in our power units. That will help the cost reduction. And also the activeness of vanadium ion inside our electrolyte can be increased. And we do have our technology and we are also improving it. So we can use less vanadium in the electrolyte to store the same amount of electricity. So that will also help the cost reduction. So I would say the cost reduction will be driven by two forces. First, technical improvement and future development. Secondly, economy of scale. We do see the cost will be reduced very fast in next 10 years. It has already been reduced by more than 50% in the past 10 years. And in next 10 years, the cost will be reduced further.
Okay. And RKP has deployed systems in city centers, renewable integration sites, lots of other places that you've mentioned now. Which of those projects would you say best shows what vanadium flow batteries are capable of today?
Well, for RKP, we had deployed more than 3.6 gigawatt hour of projects. So that's a lot. That covers almost all the user cases that we have identified. But if I need to choose one project to say that's the best showcase, I will say that will be the concurrent station located in Dalian, China. That concurrent station is 100 megawatt, 400 megawatt hour. That's the first vanadium flow battery station with more than 100 megawatts in scale. And also that's the first VFB station or first battery to have finished the grid scale black start. So that do have demonstrated this technology in scale, and also that's serving as a trigger demand for the industrialization of this technology. And also it provides lots of services to the grid and do prove its economical benefits and also prove the financial certainty of this technology.
And that's, if I remember correctly, that Dalian batteries is a city center site, correct?
Yes, it's a city center site. Within 500 meters, there's more than 10,000 households. Within 300 meters, there are 2 gas stations.
Okay, fair enough, good. And if the batteries are capable of lasting 25 years, as you say, what does that change then in the financial model?
Well, there are 2 things that's changed in financial model. The first, we have longer time to calculate the levelized cost of storage. We will have more electricity discharged from this battery during lifetime. So that means the electricity discharged from this battery will be cheaper. And secondly, the electrolyte using this battery actually has no life limit at all because it's the same chemical in anode and cathode. So positive and negative electrolyte, they are actually having the same chemistry. So doesn't matter how many cycles it runs, the chemistry doesn't change. And there's no life limit on the electrolyte. So there's possibility for financial institute to treat the electrolyte as an asset, and they can lease it to the end user. So they could reduce the capex of the battery even more and improve the payback period of the entire project. So financially, the long life will have 2 major advantages. First, cheaper electricity from the station. Secondly, the capex may be further reduced and the payback period can be shortened.
And for people who are unaware, vanadium flow batteries, do they use critical minerals? Are you using child labor in the likes of the Congo to mine vanadium?
Well, first of all, 100% of the vanadium RKP is using right now is from recycled steel slab. So we are using 100% recycled material to help to make our product more friendly to the environment because we are technology supposed to make our planet better. Also for vanadium, it's a very abundant resource in lots of countries, in Australia, in Brazil, in South Africa, in Russia, in China, and even in crude oil in some countries. And vanadium is if I remember correctly, ranked 17th in abundance in all elements on Earth. And lithium is ranked 33rd. So that means there's more vanadium on this planet than lithium. And well, if it's from energy perspective, it could be considered as critical mineral, but it's abundant mineral. For the source of the vanadium, normally right now vanadium is produced by steel makers, and we can recycle vanadium from steel slag. And there are also lots of unmined vanadium resource existing in Australia, South Africa, Brazil, many countries. And I don't think there will be forced child labor in Australia.
Fair enough. And what about end of life for the batteries then? What happens after that 25 years?
After 25 years, the electrolyte can be reused directly. For the other parts of the battery, there's no hazardous waste. It's just a carbon material, that's our electrode, and there will be plastic material, that's our membrane and the frame of the stack, and there will be metal, because we use copper to collect the current in the battery. So there will be copper, sometimes there will be steel, because the container shell will be steel, and also there will be some supporting structure as steel, and there will be some pump that got retired from there, but no hazardous waste as well. So most likely 100% of the battery can be fully recycled, and the electrolyte in the battery can be directly reused.
And are there ways of reducing the upfront cost of vanadium flow batteries? Do you do like battery as a service kind of thing?
Right now, for RKP, we are battery manufacturer. We do not do battery as a service, but we have done electrolyte leasing, working together with our financial partners. Our financial partners, they do see the value of vanadium, and the vanadium is a public traded commodity. So they decide to hold the vanadium electrolyte inside our battery as an asset. And then that will reduce the capex of the battery by more than 50%. With longer duration, the greater the reduction, because longer duration will use more electrolyte. That has been done in commercial projects in both front of the meter and behind of the meter user cases. And as a result, in both user cases, the financial performance of the project has been significantly improved. Internal rate of return has been improved by more than 2% in both user cases, and also the payback period has been reduced. So we do see there will be innovative commercial models that will help the deployment of this battery and also help people to use more renewables. And that will make our electricity from renewable more affordable.
And you mentioned earlier I think it's called Wunayushi Wind Project, which has been operating since 2012 with 100% capacity retention after 13, 14 years. What lessons have come out of that project?
Well, I would say the biggest lesson we learned from that project is we need to do standardization. That project is one of the earliest projects that we have deployed. Back then, we don't have containerized solution. We have standard stack manufacturing in our factory, and then we do all the piping, all the wiring, all the connection on site. We thought it could be more flexible, but then we learned the lesson that standardization is more important than flexibility on site, because there will be thousands of piping connections, and there will be lots of wiring points, and on-site quality control will be very challenging. So we do see some mistakes there, and we do see some errors, and we have to spend more time and more effort to correct them afterward. So after that project, we decided to move into fully containerized solution to have industrial scale FAT process and to test every stack that leave our factory to ensure the reliability. Because after all, for a battery system, for energy storage system, the weakest battery in that string decides the performance of the entire string. So right now we think standardization will be the key for commercialization and for the performance of the battery system.
Makes sense. And what has been harder to scale? Is it battery technology, project economics, supply chain, something else entirely?
I would say it's a combination of all of them. But the hardest part will be the supply chain. But luckily, we already have solved that problem, because at the beginning, no one is producing this battery at scale. So it's super hard to find suppliers. Sometimes we are required to do the manufacturing of some parts we are not supposed to manufacture by ourselves. But luckily, we solved the problem by develop project in mega scale, in hundreds of megawatt hour scale. So we have a trigger demand. So we start a really industrial scale production, and then we attract enough suppliers. So step by step, and also we build our own electrolyte facility. Right now it's operating at 4.5 gigawatt hour of production capacity per year. So then we have the supply chain established, and then we can support more peers. For RKP right now, we are also supporting other VFB manufacturers on electrolyte and some core components. So we want to see more peers, and we are willing to share our established supply chain. So that we hope that will make the scale up of this industry easier for everyone else. Then we can make this industry a better industry for everyone.
And where do vanadium flow batteries fit best over the next decade? Would it be utility grids, industrial users, data centers, islands, remote grids, something else entirely?
I would identify 3 top priority markets. First, that will be utilities, because this battery will provide the resilience utilities and the grid operators require. Secondly, I would say remote areas, for example, islands, remote mining sites. Right now, they will have option as distributed power generation. They don't need to rely on grid. We can provide stable off-grid options for them. And thirdly, I would say AI data centers and the emerging energy consuming industries, because this battery will definitely improve the power quality and also provide them with most economical solution for their power supply.
And which markets are moving fastest today and why?
Well, it's hard to say that all the markets are moving very fast because we are in a transition period. Right now, everything is under transition. So it's hard to say which one is moving the fastest. So right now, everything is moving very fast, and we need to work in full speed to make sure we can keep up with the speed of the industry and of the customer.
And if listeners stopped thinking of batteries as backup and started thinking of them as grid infrastructure, what would change?
Well, I don't think anything will change, because for our listeners and for end users, people just need stable electricity. They don't care where that electricity is provided. As long as it's clean, it's stable, it's affordable, people doesn't care. So it's our job to make sure people does not feel the transition, especially for the end customer. We do not want them to feel the pain of transition. There should be smooth and seamless transition, and then we switch to clean, stable, and affordable electricity supply. So it's our job to make sure that happens. That's why we believe vanadium flow battery could be an accelerator for our net zero targets, and also could be an accelerator for the electrification in many sectors.
We're coming towards the end of the podcast now, Min. Is there any question I have not asked that you wish I did, or any aspect of this we haven't touched on that you think it's important for people to think about?
Yes, there's one thing I want to mention. Vanadium flow battery, unlike lithium battery, is providing opportunity for every country in the world to develop its own supply chain. For lithium battery, intensive supply chain support is required, and you need to have lots of supporting suppliers to be located close by the lithium battery manufacturers. But for vanadium flow battery, this is a more tough battery. This is very similar to car manufacturing. You can have automakers in many countries as long as there's local demand, because the shipping cost is very significant. And that's applies the same for our battery, because our electrolyte is 60% water and electrolyte is taking 40 to 80% of the total cost of the battery. No one wants to ship water around the world. So as long as there is trigger demand in local country, we can start the battery assembling very easily in that country. And also, as long as there's vanadium resource in that country, we can start the production of electrolyte in that country. So localization is deep in the root of this technology, and that will help every country to achieve its energy independence and to improve their energy security. So this is a very unique technology. This gives equal chance to lots of countries. And also the supply chain is relatively not easy, but relatively easier to be localized and to be built in a country. So I would say this is a very important factor I want our listener to know. And this is something we are also telling the same stories, the same ideas to lots of government agencies and lots of policymakers in the world.
Fascinating. Great. Min, that's been really interesting. If people would like to know more about yourself or any of the things we discussed on the podcast today, where would you have me direct them?
Well, my LinkedIn profile, if people search Rongke Power on LinkedIn, Rongke Power RKP, or my name on LinkedIn, it will show up. Please feel free to contact me via LinkedIn. And we have our company website. Feel free to drop a message.
Great. I'll put those links in the show notes as well, so everyone will be able to get them in. Thanks very much.
Thank you.
Min, that's been really interesting. Thanks so much for coming on the podcast today.
Thank you, Tom. Thank you for having me. It's really a pleasure to talking to you.